Take a look at normalization. So the normalization of an integral domain, to begin with, is the integral closure of that integral domain in its field of fractions. If you feel that you need to repeat the basic theory of integral extensions, feel free to do so by going back to the appropriate lecture. Otherwise, the normalization is the integral closure, meaning the set of all elements in the field of fractions of S that are integral over S, meaning that satisfy an harmonic polynomial equation over S. And this is a ring extension of S. So S prime is a normal integral domain. Normal means that it's integrally closed within its field of fractions. We will use the same terminology for varieties. So if S is the coordinate ring of some variety x, and S prime is the coordinate ring of some variety x prime, which they are by the equivalence between rings and varieties. But the point is, if this is the case for the specific x and x prime, then we say that x prime mapping to x, this map corresponding to the ring extension, is the normalization of x. And we call the variety normal if its coordinate ring is normal. So our first theorem is that the normalizations that we will be using are finite. This does not hold in general for general normalizations, but in this following setting, that if you have S a finitely generated K algebra, K is as usual our algebraically closed field, and assuming that S is an integral domain, then the integral closure S prime of S in any finite field extension L of its fraction field is a finite extension ring of S. That's a lot of words, so let's take a look at it. So we have here S, and we have the fraction field of S. What we want to show is that if we take S prime, the integral closure in the fraction field, then it is a finite extension ring. We will have to show something more in order for the proof to work. We will have to show that if we take any slightly bigger field, L, and we look at the integral closure of S in L, then this will be a finite extension ring over S. And now you might protest and say, didn't we prove that integral extensions are finite? No, we proved that a ring extension is finite if and only if it is generated by finitely many integral elements. But this doesn't mean that whenever the whole ring extension is integral, so every element in the ring extension is integral, then it must be finite. But in this case, it is. The key to proving this theorem will be use of the Noether normalization theorem. So Noether normalization theorem tells us that this ring S is a finite extension of some polynomial ring. And polynomial rings are integrally closed. So they are normal. They are integrally closed in their field extension, which is the rational function field in these indeterminates. And also, the closure, the integral closure of S in this field L is equal to the integral closure of the polynomial ring in L. Pause a bit to think what this means and why this is true. So the reason is that S is finite over this ring, so it is an integral extension over this ring. In that direction, we do have a result. And so this means that if I want to enlarge this polynomial ring by adding integral elements, I will add all the elements of S to begin with. And so I will be past S. And using the properties of integral extensions with respect to composition and so on, this implies that the integral extension of S in L is the same as the integral extension of the polynomial ring in L. And also, the field L being a finite extension of the fraction field of S, and S being finite over the polynomial ring, I know that the field L is a finite extension field of the rational function field, the quotient field of the polynomial ring. So this is finite. This taken together means that it's enough to prove the theorem in case S is already normal. And I will sketch the proof in this case. I will sketch the remainder of the proof. So the first thing that you do is that you prove that L as an extension of the fraction field of S has a basis. Well, of course it has a basis. It is a finite field extension, but you can choose these elements of the basis in S prime. The reason for this is that if I take, so a priori the elements are in L, but I can choose them in S prime. The reason is, if I take some V in L, then I have an equation of the form A naught V to the N plus etc. plus AN equal to 0, because the field extension is algebraic, and these AI belong to S. But this means multiplying by V to the power, by A0 to the power N minus 1, I get that A0 V to the power N is integral over S, so it belongs to S prime. And so this means that I can do this to all of my basis elements, tweak them so I get something in S prime. The second thing that I show, and this requires the assumption that L is separable, which we do not assume for the theorem, but I will say something about that very little later. So what I do is that I know that this basis has a dual basis. So I have a dual basis, V1 to Vn, that I can also tweak to be in S prime. And why do I need separability? Well, what I'm using is the bilinear form, the trace form of L over K of the product of two elements. This is a non-degenerate bilinear form, so I get a dual basis. So how does this help me? Well, if I take an x in S prime, then I multiply x by ui and take the trace. I'll skip the subscripts. If I then expand this in this other basis, then this will be the trace of xj ui vj. But since these bases are dual, moving out this xj, I get this trace of the product, which is the Kronecker delta. So this is nothing but xi. What did this give me? Well, I know that this thing is in S prime, because ui are in S prime. So the trace of an element in S prime will in fact be in S. This follows, not trivially, from results about the trace being a coefficient of the minimal polynomial and results about how the minimal polynomial behaves with respect to such normal rings. And so this means that this xi belongs to S for all I, meaning that the basis vi, v1 through vn, is a finite basis of S prime over S, which exactly says that S prime is a finite extension. In the case when L is not separable, you need to do some tweaking. I will not go into that, but the result holds as well. So as a result of this, we know that if you have an irreducible affine variety X, then the normalization is finite. So this is exactly what we proved earlier, just dualizing it, looking in the category of varieties. And since we know that finite maps are proper, then we are one step closer to proving that the normalization is a desingularization, which is our goal for curves. So now we know that we have the normalization being finite. Perhaps more importantly, the main theorem we'll prove is that normal curves are smooth. So then the normalization of a curve being normal will be smooth. This applies only to curves. And so what we'll do is we will start as usual with affine curves. So we take C, an irreducible affine curve, call its coordinate ring R and its fraction field Q. The way we'll prove this will also give us a construction of the normalization. So we want to prove that if C is normal, then C is smooth. Equivalently, if C has a singular point A, then C is not integrally closed in its field of, so the R, is not integrally closed in its field of fractions. Now remember that smoothness amounts to the fact that the vanishing ideal of a point A satisfies the property that this vector space has the same dimension as the codimension of the point in the variety. Since the variety is an irreducible curve, for smoothness, this has to be 1. So in the proof, I'm assuming that I have a point that is singular. Then I know that this thing has dimension at least 2. So I can find x and y in I of A so that their classes in this quotient are linearly independent. Assuming that I do have such linearly independent elements, I will prove, or I will rather construct, a strange element that is not in the ring R, so an element of the field of fractions that is not in R, but that is integral over R. So showing that R is not normal and therefore C is not normal. What I do is I divide y by x plus alpha y, where alpha belongs to the base field, and all of this I multiply with some element u belonging to R but not to the maximal ideal of the point A. So why is this not in R? So why is this element not? Well, if it were, in R, then I could multiply by the denominator and get here x plus alpha y times r. And this element, of course, this is the element y times u. This belongs to r, so I get something in the ideal generated by x plus alpha y. Now, when I pass to this quotient, then I get that this yu is a multiple of, so is some lambda times x plus alpha y. Well, that is because any element in R is something in the, so R mod I of A, this is isomorphic to K. So any element of R acts as a scalar on this vector space, because what is not in K is in the ideal, and multiplying it by things in the ideal brings me in the ideal times itself, so it dies in this vector space. So this has to be some L in K. And y of u, again, for the same reason, this means that I have mu times y is equal to lambda times x plus alpha y, where mu is, so to speak, the R mod I of A part of u. And this is not zero because u is required not to be in the ideal. So a non-zero multiple of y has to be a multiple of this element, and this cannot happen because of linear independence. So this shows that this element is not in R. What I now need to show is that this element is integral over R. So I need to show that this element is integral over R. So I have my elements x and y in this ideal I of A that I view as elements in the field of fractions. In the field of fractions, this is nothing but the rational function field of my curve C, because R is the coordinate ring of C. And this has transcendence degree 1 over K. This is not something we have gone through in detail, but this follows from the dimension being 1. And so this means that these two elements have to satisfy some algebraic equation. So I have f of xy equals to 0 for some polynomial equation. Because otherwise, if they were both transcendental, this means that this field has a higher transcendence degree. So this I take fm of xy to be the minimal degree homogeneous term of this polynomial. If you think about it, and please do pause and think about it, if you make a change of variables, keeping the variable y, but changing x to x plus alpha y, and y is still to y, then after this change of variable, the coefficient of y to the m in this thing will be f of f of alpha 1, f m of alpha 1. So knowing this, remember from when we proved Noether normalization, we saw that if we have a homogeneous polynomial, which this is, then we can always choose the first coordinate so that when the second coordinate is 1, this thing is non-zero. So for some alpha, this fm of alpha 1 is not 0. Since I'm in a field, I can divide through this constant, so I get that this f of xy will have the term y to the power m plus some terms, other terms, of the form my new x variable to the power I plus y to the power j of degree at least m. So this is not enough to say that y is integral or whatever, because, I mean, y is already in R. But these might have higher degree, that is the point. Write this by moving ym to one side, and so on. I get ym times y plus some polynomial xy plus y to the power m minus 1 times x plus alpha y times some other polynomial y, and so on until the final term is x plus alpha y to the power m some polynomial g naught. And this is equal to 0. I just rewrote everything. And by moving coefficients around, I can assure that this gm of x comma y, well, to begin with, doing this, because I have a 1 here plus terms of higher degree, this will be in the non-constant part. So it will contain multiples of x and y, so this will sit inside my ideal, I of a. And for these other gi, I can choose as polynomials. So for I smaller than m. And now I set u to be equal to 1 plus gm of xy. Because gm of xy belongs to the ideal I of a, and 1 does not, u cannot belong to the ideal. So this is exactly as the element u that I wanted earlier. And so this means that so I get here y to the power m times u plus y to the power m minus 1 times this x plus alpha y times something, and so on. By dividing through by x plus alpha y to the power m and multiplying as needed by enough powers of u, so rearrange. Then I get that y divided by x plus alpha y for this choice of alpha times u for this u is integral over R. I get a monic polynomial relation for this element. And at the end, it was a bit technical, but the point is I rearrange terms and then I get my result. So this shows that a normal curve is indeed smooth, because if it is not smooth, then I can find such an element that is not in R, but that is integral over R. So R is not normal.